For more videos like this for Discrete 1, you can take a look at Sarai Studies, link is in the description box below.
In the last two videos, I introduced what sets are and I taught you how to describe sets individually. But what if you want to describe the relationship between sets? So let's say you have a set A and a set B. How can you describe the relationships between these sets if there is a relationship in the first place? Well, there's only three types of relationships we have to worry about. Now, a useful skill you want to know in order to understand these types of relationships better is how to visualize these sets. Now, a way to visualize these sets is using Venn diagrams. So let's say you have a set A that contains the elements 1, 2, 3, and 4. Visually, you can represent set A as a circle in space, label it A, and that circle is just going to contain the elements of A. So 1, 2, 3, and 4. And if you have a set B that is equal to the numbers 10, 20, and 30, visually, that's just going to be represented by a circle in space. You can label it B, and B is just going to contain the elements of B, 10, 20, 30. So keep that in mind. The first relationship between sets is when set A is a subset of set B. This just means that all of the elements that are in set A are also in set B. Now, these relationships are not commutative, meaning that it doesn't mean the opposite that B is a subset of A, so keep that in mind. And think of this symbol as a less than or equal to sign, so there's only two options visually. And the first option is that A is smaller than set B, so you'll have B as the bigger one, and A will be strictly smaller. Now, why don't I draw A over here? Because the definition of a subset means that all of the elements in A are in B, so everything inside A will be inside B, so it won't be outside of B. The second option is that you have A being the same as B. So yes, all elements of A are and B, but they're the same, for then A will also just be the same circle. Now, thinking of this as a less than or equal to sign, wherever the alligator mouth is open towards, that's what we call a superset, and the other side is a subset. Now, the other two relationships are literally just this one and this one. This here is a combination of the other two. So the second relationship between sets is when set A is a proper subset of B. So if this was less than or equal to, this is just the less than part. So this is when set A is strictly smaller than set B. So visually, set A is literally smaller than set B. So that's this right here. So all of the elements in A are in set B. It's just that they cannot be the same set. So it can't be this case. Now, the third type of relationship is when A is equal to B. So we're taking care of this equal sign here. So that's just going to be this one, where A is the same as B, and vice versa. B is the same as A. Now, note, when you see this symbol, yes, you can think proper subset, but that doesn't mean that when you see this symbol, it means improper subset. No, remember that this symbol just represents the two types of relationships that you can have. Either you have a proper subset, where you properly have a set that's smaller, that's sub than the other one, where all of the elements in A are in B, so all of the elements in A are still inside B, but it's never the same as B. Or the improper subset, where yes, all of the elements in A are in B, all of the elements in A are in B, so it's still considered a subset, but it doesn't really make sense because at the end of the day, they're just the same, so you could just say that they're equal to each other, which is why we call it an improper subset. So now that we have the picture as to what the relationship between these sets look like, how can we define these relationships mathematically? Because this is the important part. You will be using these definitions once we get to doing proofs with sets. So for the first relationship, just look at the picture. What does it tell you? It tells you that if you have any element in set A, then it will also be in set B. And look, it's still in B. We can represent these elements as X. So A is a subset of B if and only if, that's what we use for definitions, for all elements, for all X. If that X is in set A, then that implies that that same X should be in set B, which also satisfies this case. If there's an X in set A, which is this one, then it should also be in set B, which is this one, and it is. For the second relationship, A is a proper subset of B, and we're going to say if and only if what? Well, it's the same thing that we had over here. I'm just going to copy and paste exactly what I had here. Again, this says that if we have some X as an element in set A, then that implies that that same X is also an element in set B, which it is. Look, it's still an element in B. But there's one more thing we have to take into consideration. This satisfies this condition as well, where A is essentially equal to B. But if we're thinking of this as less than or equal to, and here as just less than, there is no equal option here. We can't have this case. So how can we make sure that this is true, but also this is not true? In other words, how can we make sure that A can never be equal to B? Well, the only way that A can be equal to B is if A has all of the elements that B has. So you can think of A as stretching out because it contains everything that B has. Like that, then A is equal to B. So to stop that, we have to have some value, some other element, let's call it Y, where A can't stretch to contain Y because it's not in A. It's only in B, and so therefore A will never be able to stretch all the way so that it's the same as B. So this should be true, but there must exist some element y such that y is an element of set B, but it is not an element of set A. So it will never be an A, so therefore A will never be the same as B because they won't have all the same elements. And finally, for the last relationship, we can just say A is equal to B if and only if for all elements in A, they are also in B, and vice versa. For all elements in B, they are also in A. So that would mean that for every x, for all x that are elements of A, that implies that it has to be an element of B, and for all x that is an element of B implies that it has to be an element of A. But notice how this is a definition of a subset. So really, we just have to prove that A is a subset of B. And then if we just switch these, B is a subset of A, that would give us the opposite. So in other words, for all x, we have to prove that A is a subset of B and B is a subset of A. In other words, all elements of A are in B and all elements of B are in A. That means that A and B are equal to each other. So now we're going to practice, given these sets, answering the following questions with true or false. So we can do this two ways, either visually with a Venn diagram or the literal way, which we'll talk about after. So with the Venn diagram, you just draw your sets. So I always like to start from the bigger sets and then to the smaller ones. So set C we can represent by drawing a circle in space and labeling it C and just put all of the elements of C inside. So 1, 2, 3, 4. Set B happens to also have 1, 2, 3, 4, meaning that they're the same set. So this is also set B. And then set A happens to only contain 1, 2. So we can see that this circle in space that contains only 1 and 2 is set A. So this is our Venn diagram. So we're going to use this Venn diagram and the fact that we can think about these symbols as less than or equal to or just less than to answer these questions. So for the first one we have, is set C smaller than or equal to set B? Well, set C is this one right here, and it's actually equal to set B. They're the same. So because it satisfies this condition, this whole thing is true. Is set C smaller than set B? Well, set C is right here. Set C is not smaller than set B. They're the same. So this is false. If it was this, like it was over here, then it would be true, because the condition that C is equal to B would be true. Is set A smaller than or equal to set B? Well, set A is this one right here, and it definitely is smaller than set B, so that would be true. Is set A smaller than set B? Well, we just found that was true. Set A is definitely smaller than set B, so that's true. Is set B smaller than or equal to set C? Well, set B is this one right here, set C is this one right here. They're the same. They're equal to each other, so because this condition is satisfied, it is true, not because set B is smaller. Set B is not smaller. They're the same. Is set B equal to set C? Yeah, they're the exact same set, so true. Is set B smaller than or equal to set A? Well, set B is right over here, and set A is right over here. So set B is not smaller than, it's actually bigger than set A. So this is false. Now the literal way is literally using the definition. So for part A, we have set C is a subset of set B. If that's true, then the definition of a subset says that all of the elements of C must be elements of B. Is that true? Well, set C has elements 1, 2, 3, and 4. Are these elements in set B? Well, I see 1, 2, 3, and 4 in set B, so yes, that is true. Now the difference here is that C is still a subset of B, but specifically it's a proper subset of B. But disregarding any vocabulary, and to get to the point, the only difference between these symbols is the equal sign. There's no equal sign, which should remind you, oh, these sets should not be equal, and if they are, then the whole thing is false. So just think, anytime you see the symbol, check if the sets are equal. Are sets B and C equal to each other? Yes, so therefore the whole thing is false, because this is not looking for equal sets. If it was, then it would be looking like this, and it's not. We're looking for this set to be strictly smaller than this one, not the same. And that will never be the case, because if they are the same set, then this will never be smaller than this one, since they're the same. They'll be the same size. So this whole thing is false. Here we have A as a subset of B. Okay, so that means that all of the elements in A are supposed to be in B. Is that true? Well, set A has elements 1 and 2. Are these elements in set B? Well, yes, I see 1 here, 2 here. They are in set B, so therefore this is true. Here I have A is a subset of B, specifically a proper subset. Okay, check. Are these equal to each other? Set A and B, are they the same? Are they equal to each other? No. So the only way it's true after that is if it satisfies the definition of a subset, which is that all of the elements in A are supposed to be in B. So is that true? Well, again, all of the elements in set A are only 1 and 2. Are these in set B? Well, 1 is here, 2 is here. Yes. So this whole thing is true. Here we have B as a subset of C. That means that all of the elements in B are supposed to be in C. Is that true? Well, set B is right here. The elements are 1, 2, 3, and 4. Are these elements in set C? Well, 1 is here, 2 is here, 3 is here, 4 is here. So yes, it is true that B is a subset of C. Are B and C equal to each other? Yes, they are literally the same sets. So that's true. Here we have B as a subset of A. Well, that means that all of the elements in B are supposed to be in A. Is that true? Well, B has elements 1, 2, 3, and 4. Are these elements in set A? Well, I see 1, I see 2, but I don't see 3 and I don't see 4. So because not all elements of B are in set A, this is false. B is not a subset of A. And that's it for this video. In the next video, we're going to have an ultimate practice of differentiating between all of the symbols we've already learned so far. And then in the video after that, we'll finally start talking about operations of sets, so union, intersection, and so on.